Welcome to AI Paper Podcasts, where we dive into the latest AI and tech research and really pull out the core insights for you.
That's right. No fluff, just the key stuff.
Exactly. And today, we're looking at a really fascinating paper. It's called Mathematical Research with GPT-5, a Malliavin-Stein experiment.
Ooh, okay. Sounds heavy.
It kind of is, but super interesting. They basically threw GPT-5 into the deep end of advanced math. Specifically, they tested if it could tackle an open problem using something called a Malliavin-Stein framework.
Right, the Malliavin-Stein method, yeah. Powerful stuff in probability.
So you probably remember back in August 2025, there was that big stir on social media. Sebastian Bubeck posted on X that GPT-5 Pro had supposedly solves an open problem in convex optimization.
Oh yeah, I remember that. Improving a bound, like instantly. Screenshots everywhere.
Totally went viral. Well, this paper we're discussing today, it was directly inspired by that whole event. The researchers here wanted to see for themselves in a controlled way if GPT-5 could really push the envelope.
So not just take someone's word for it on social media.
Exactly. They set it a specific task. Take a known qualitative fourth moment theorem and make it quantitative with explicit convergence rates, something they believed hadn't been solved before.
Okay, so a real test. What did they find? Did it work?
Well, yes and no. The findings are pretty nuanced. GPT-5 made, significant progress in both Gaussian and Poisson settings. It often suggested the right kind of approaches.
There's always a but with these things, isn't there?
Right. But it needed constant, really precise human guidance. It made critical errors that it couldn't spot on its own. It needed someone to point out exactly where it went wrong.
So more like a junior assistant, maybe. Not really solving it autonomously.
That's exactly how the authors put it, a junior assistant, which is impressive in itself, but yeah, not an independent researcher.
And that has bigger implications, I guess.
Huge implications. It suggests AI, right now anyway, is maybe stronger at what they call incremental research, building on existing ideas.
Rather than like generating completely new breakthroughs from scratch.
Precisely. And it raises some tricky questions, like what happens if AI starts flooding the zone with technically correct, but maybe not super insightful papers? And how do we train new researchers, PhD students, to develop those deep critical thinking skills if they can just sort of ask an AI?
Yeah. That's a lot to think about. Definitely worth diving into the details.
Absolutely. So let's rewind a bit to that initial GPT-5 convex optimization thing that Bubeck posted. You mentioned the buzz, but what was the reaction like comparing, say, the general public versus actual mathematicians?
Oh, it was night and day, really. For non-specialists, people on social media, it absolutely felt like a watershed moment. Like, wow, AI is competing with mathematicians now, solving open problems. It seemed huge.
Yeah, the headlines were pretty dramatic. AI solves math problem humans couldn't. That kind of thing.
Right. But then you had the actual experts in the field, like
Right.
Ernest Ryu, who weighed in.
And he wasn't quite as blown away.
Not in the same way, no. He offered a much more nuanced view, as the paper puts it. He pointed out that GPT-5's proof relied heavily on a well-known tool called Nesterov's theorem.
Okay, so not some obscure thing, but a standard part of the toolkit for that area.
Exactly. Ryu's take was basically, yeah, it's impressive it could assemble the pieces, but an experienced human researcher familiar with Nesterov's work could probably have gotten a similar result in, a few hours.
So less AI genius and more very fast application of known techniques.
Something like that. Still impressive technically, but not the fundamental breakthrough some perceived.
And that gap in perception between the public hype and the expert analysis, that's what led these authors to do their own test run.
Precisely. They thought, okay, let's take this capability, but apply it to our field, the Malliavin-Stein method, where we know the landscape inside out, and see what it can really do on a problem we know is open.
Right. But before we get into their experiments, maybe give us the quick version. What is the Malliavin-Stein method? It sounds pretty intense.
It is, but the core ideas are really elegant. It's basically a super powerful toolkit from probability theory. Its main job is to help you figure out if some random thing like the result of a complex process is getting closer and closer to a standard normal distribution, the bell curve.
Okay, so measuring convergence to Gaussian.
Right, but it's more than just if it converges. It combines two key ideas. First, there's the Stein method. This is amazing because it doesn't just say yes or no to convergence. It actually gives you a rate. It tells you how fast it's converging.
So it's like having a speedometer for how quickly something's becoming normal.
Exactly. It quantifies the speed. Then you have Malliavin Calculus. This is like calculus, but for random variables. It gives you a way to differentiate and analyze the structure of these random objects, especially in things called Gaussian and Poisson spaces.
Okay, so Stein gives the speed, Malliavin gives the tools to analyze the random stuff itself.
You got it. And when you put them together, the Malliavin-Stein method, you get this incredible power to not only prove convergence, but to derive explicit quantitative bounds on the rate of convergence. Real numbers, real formulas.
Which is way more useful than just knowing it converges eventually.
Absolutely. So the challenge they set for GPT-5 was take this existing theorem by Bass O'Connor and others, which was qualitative. It just said, yes, convergence happens under these conditions, and turn it into a quantitative one. Find the actual rate, a problem they believed was still open.
Okay, that's a serious challenge, not just summarizing, but generating a new quantitative result. So how did GPT-5 do on its first try? In the Gaussian setting, what was the prompt?
They gave it a very specific prompt. They asked it to get a quantitative version of that theorem for a sum of two things called Wiener-Ito integrals. Think of them as building blocks for random processes. One integral had an odd order, p, the other an even order, q.
Okay.
And critically, they told it to use the Malliavin-Stein method and make the final convergence rate depend on something called the fourth cumulant of the sum.
The fourth cumulant. That tells you about the shape, like the tails of the distribution, right?
Exactly. It measures deviation from the normal shape. So the prompt was very targeted.
And GPT-5's first swing.
The author said it was strikingly effective. It picked the right tools, the right overall approach. It looked really promising.
Wow. So it understood the complex setup.
It seemed to, yeah. But then, as they dug into the math it produced, they found an error. A small but absolutely critical reasoning error in a specific formula, the covariance between y squared and z squared.
Ah, the devil in the details. One wrong step and the whole proof collapses.
Precisely. If they hadn't caught that, the result would have been wrong.
So how did they get GPT-5 to fix it? Did they just say, check your work?
They tried that first. They prompted it to check its formula. But interestingly, GPT-5 came back with another incorrect version.
Seriously. So just asking it to double check wasn't enough.
Apparently not for this kind of subtle error. It wasn't until the researchers got much more specific, basically saying, hey, look at this specific equality in your calculation. Is that really true?
Pointing directly at the mistake.
Exactly. Only then did GPT-5 seem to recognize the issue. It responded, admitting the statement was false, which, aligns with its training to agree with user corrections, and then it actually provided the correct reasoning and the right formula.
That's fascinating. It highlights this need for very precise human oversight, especially for those subtle logical flaws. But okay, after that crucial fix, they got to Theorem 2.1. What's the takeaway from that theorem?
So Theorem 2.1 for this Gaussian case essentially says, if you have this sum z made of an odd order integral x and an even order integral y, with total variance normalized to 1, then the distance between z and a perfect standard normal distribution measured by something called the total variation distance is bounded.
Bounded by what?
It's bounded by the square root of 6 times the fourth cumulant of z. So square root of 6 kappa 4 of z.
Okay, let's unpack total variation distance and fourth cumulant just a bit more.
Sure. Total variation distance, think of it as just a strict measure of how much two probability distributions differ. A small value means they are very similar. And the fourth cumulant, kappa 4, as we said, measures the tailedness, how much the tails of z's distribution differ from a Gaussian's tails.
Got it.
Yeah,
So
yeah.
the theorem puts a hard upper limit on the difference from normal based directly on this shape measure, kappa 4. Smaller kappa 4 means provably closer to normal.
Precisely. And the proof itself, which GPT-5 helped construct under guidance, had some neat steps. It used the main Malliavin-Stein machinery, controlled some variance terms.
Right.
But a really key insight was what they called the parity-driven fourth cumulant decomposition. Because x was odd order and y was even order, these tricky cross terms, like the average of x cubed times y, just disappeared. They vanished.
Ah, because of the odd-even combination.
Exactly. That simplified the fourth cumulant of the sum z enormously. It just became the sum of the individual fourth cumulants plus this covariance term they had to fix earlier. And crucially, all those terms were non-negative, which allowed them to get the final bound.
So that odd-even structure was really leveraged to make the math work out cleanly.
Nice. Did GPT-5's contribution end there?
No, actually. After getting the theorem nailed down, The researchers asked it to format the whole thing like a research paper.
And it could do that, intro, proof, everything.
Yep, intro, theorem statement, proof steps, even a bibliography. And then they asked it for a concluding section with ideas for possible extensions.
Oh, interesting. Did it suggest anything useful?
It did.
Here.
One of its suggestions was basically, hey, you could try exploring this in non-Gaussian frameworks. And that suggestion directly led them to the next part of the experiment, the Poisson case.
Wow, so the AI itself pointed the way to the next research question. That's pretty cool. It shows it can identify like natural next steps.
Yeah, it suggests it understands the landscape well enough to see adjacent possibilities. Okay, so moving to the Poisson setting. This is often trickier than Gaussian, right? What new challenges popped up?
Definitely trickier. The underlying structure is different. So the new prompt was to extend the theorem to the Poisson case, and they pointed GPT-5 to a specific reference paper.
And did it pick up on the differences?
It did, quite quickly actually. It recognized a key structural difference. In the Poisson world, that mixed term EX3Y doesn't necessarily vanish like it did in the Gaussian case. That immediately flags the problem as potentially harder.
So it spotted a complication. Good start. But did it miss anything this time? Another blind spot.
Yes, and it was a significant one again. It completely overlooked the fact that the covariance term, Convex2, Y2, is still non-negative, greater than or equal to 0 in the Poisson setting, just like in the Gaussian one. This is a known property.
It missed that. How did that come up?
The researchers asked it directly, something like, is Cov x2, y2 non-negative in the Poisson case? Can you show why or provide a reference? And GPT-5's response was basically short answer, no.
Whoa. It just confidently said no to something that's actually true.
Yeah, and apparently gave a pretty unconvincing reason why not. It was just wrong.
That's a stark reminder of the reliability issue. A human expert would likely know that property or know where to look it up instantly. How did they correct it this time?
Again, it required very specific guidance. They had to point it to the exact section, literally 2.4, in the reference paper they provided earlier.
And then it got it.
Then it immediately understood the implication and confirmed, yes, Cov x2, y2 is indeed non-negative in the Poisson case too. It needed that precise pointer to connect the information it had access to.
Incredible. Okay, so after that correction, they derived the Poisson version, Theorem 3.1. What did that say? Was it similar to the Gaussian one?
Similar, but with a crucial extra condition. It basically says for Poisson integrals xn and yn with normalized variance, if those tricky mixed odd moments vanish in the limit, meaning exn3yn goes to 0 and exnyn3 goes to 0, then having the fourth moment, eZn4 converge to 3, the Gaussian value, is enough to guarantee that Zenin converges to a standard normal distribution.
So that condition about the odd moments vanishing is key in the Poisson case.
Absolutely essential. And to hammer that point home, the paper includes proposition 3.2, which is a brilliant counterexample.
What does the counterexample show?
It showed why you absolutely need that condition about vanishing odd moments in the Poisson setting. They constructed specific Poisson integrals, U and V, and found a combination, let's call it S alpha star, such that its variance was 1 and its fourth moment was 3.
Okay, so it looked Gaussian based on the second and fourth moments.
Exactly. It had the right variance and fourth moment. But crucially, they calculated its third moment, ES alpha star cubed. And it wasn't 0, it was about 0.719.
So even though moments 2 and 4 matched to Gaussian, the non-zero third moment proved it wasn't actually Gaussian.
Precisely. It demonstrated clearly that in the Poisson world, just matching the second and fourth moments isn't enough if you don't also control those odd moments. That assumption in Theorem 3.1 isn't just a technicality, it's necessary.
That really underscores the subtlety and maybe the limitations of relying solely on these moment-matching heuristics sometimes. You need deeper checks. Okay, stepping back from the specific math, what did the authors conclude about GPT-5's role in this whole process? How did they reflect on it?
Their reflections are really insightful for anyone in AI or research. They consistently describe GPT-5 as an executor or a junior assistant.
Meaning it could follow instructions, but not really lead.
Pretty much. It was good at following the reasoning steps they laid out. It could recognize mistakes when they were explicitly pointed out, and it could even suggest natural next steps like the Poisson extension. But it wasn't driving the core intellectual direction.
So the kind of research it facilitated was more incremental.
That's the term they used. Incremental research. It seems very capable of combining existing ideas, refining known results, extending things to similar contexts, but generating genuinely new ideas or fundamentally new approaches. That didn't really happen here.
Which is still useful, but maybe not the paradigm shift some hope for yet. What about the idea that AI saves time? Did it speed things up for them?
This was one of their most interesting observations. Often, no. They found that the sheer effort required to carefully verify everything produced by the AI, to double-check every line of reasoning, and to provide that constant, precise guidance actually made the process slower in practice than if they'd just done it themselves.
Wow, okay. The verification overhead basically canceled out or even outweighed the generation speed. That's a crucial point missed in the hype.
It really is. It's not just about output speed. It's about the total human time investment to get to a correct and reliable result.
And this experience led them to identify some potential risks for the future of research, didn't it?
Yes, two main ones. First, the risk of a proliferation of incremental results. If AI makes it easy to churn out lots of papers that are technically sound, but maybe only moderately interesting or derivative,
It could just flood the scientific literature, making it harder to find the real breakthroughs, like adding noise.
exactly. It could saturate the scientific landscape, as they put it, diluting the impact of truly original work.
That's a serious concern. What was the second risk they highlighted?
It was about the training of new researchers, particularly PhD students in math and potentially other fields too.
How so?
Well, traditionally, a huge part of becoming a researcher is the struggle, right? You wrestle with problems, you make mistakes, you go down dead ends, you learn to find your own way, develop your own intuition.
That's where the deep learning happens, for humans.
Precisely. Their concern is that if students become too reliant on AI to just, generate proofs or arguments quickly, they might miss out on developing those fundamental skills. It could lead to a weakening of the very process of becoming a mathematician or scientist. Less resilience, less independent critical thinking.
Losing the benefit of the productive struggle. That's a really profound worry for education. So, wrapping things up, what's the final verdict from this experiment? Is GPT-5 a mathematical genius in waiting or just a fancy calculator?
Well, the authors are careful not to be too definitive, but they do stress that GPT-5 is a significant improvement over previous models like GPT 3.5 and 4, and that progress happened fast. So the trajectory suggests more advances are coming.
But it's not replacing mathematicians tomorrow.
Not based on this, no. It's a powerful tool, an assistant, an executor, but the need for human insight, guidance, verification, and especially the ability to spot subtle errors or generate truly novel concepts. That seems firmly in the human domain for now. The question of whether AI can substantially displace mathematicians, they say, remains open.
So this has been a fascinating look under the hood. We've seen GPT-5 handle some really complex math, extending theorems, suggesting research directions, but crucially, only with intense human partnership. It stumbled on errors a human expert would likely catch and needed precise pointers to correct its course.
Right, it's powerful for that incremental work, exploring known paths, but maybe not yet forging entirely new ones independently.
Which leaves us, especially those of you working in AI and ML, with a big question to ponder. As these models get undeniably better and faster, how does our definition of original research change?
Does the value shift more towards the conception of the truly new idea rather than just the technical execution?
Maybe. And if generating technically correct derivations becomes easier, how do we ensure we're still training the next generation of researchers to have that deep critical thinking, that ability to question, to struggle, to find the genuinely novel insights that AI, at least currently, seems to miss? How do we navigate this evolving landscape?
That's the million-dollar question, isn't it? Something we'll all need to grapple with as this technology continues its rapid advance.